So today's lesson is going to be on disproving conjectures, or trying to decide whether the conjecture is true or false. In this case, because we're trying to disprove the conjecture, we are trying to show that the statement is false. So what we're going to do to show that the statement is false is we're going to find a counterexample, and this counterexample will show that the statement is false because it won't satisfy the given statement that we have. So let's look at an example. Odd whole numbers less than 10 are prime. This is my conjecture right here. Odd whole numbers less than 10 are prime. So what we don't need the observations here, but we've already talked about them. Let's look at a counterexample statement. So when we're trying to decide the counterexample statement, we're trying to say that the result of the statement, so the prime part of it, is not true. So our counterexample statement would be odd whole numbers less than 10, that's the condition, that's what needs to be true, are, and instead of putting prime, we're going to say not prime. Okay, so let's think about this. A prime number is a number that has only two factors, the number and itself. Okay, or sorry, the number itself and 1. So 7, for example, is a prime number because I multiplied to get to 7 by 1 times 7, and therefore 1 and 7 are factors of 7, and the numbers that are factors are only 1 and itself. So this would be a prime number. 9 would not be prime because I can have two ways to multiply to get to 9. I have 1 times 9 or 3 times 3. So my factors of 9 are 1, 3, and 9. And because it has more than two factors, it's not prime. Okay? So let's look at some observations. Let's look at all the numbers that are less than 10, that are whole numbers, that are also odd. So 1 is an odd number, 3 is an odd number, 5, 7, and 9. So these are all the odd numbers that are less than 10, odd whole numbers less than 10. Now, what I want to try to show is that there's an odd whole number less than 10 that is not prime. So when I look at these numbers, 1 is not prime. It's kind of a weird example. It's not prime because it only has one factor. And 9 is not prime because, again, we talked about we can use 3 times 3 to multiply to get 9. So my counterexample here would be 9 is a odd whole number that is not prime because it has three factors, which are 1, 3, and 9. So the example 9 is my counterexample. It satisfies the assumption of the question. So this part here represents my assumption, and then this part here represents my conclusion. So the assumption is true, but the conclusion is false. Let's look at another example. My conjecture here is the sum, so that's me adding two prime numbers is an even number. Okay, that's the statement that I've been given. And I want to find a counterexample, which means I want to show that this statement is false. So again, here's my conclusion of the statement. Here's my condition of the statement. I need my condition of the statement to be true. So let's write what we're trying to find. We're trying to find that the sum of two prime numbers So that's my condition. That still needs to be true. We need them to be two prime numbers. And instead of the conclusion being true, we want the conclusion to be false. So we want the conclusion to be is not an even number. So we can put the word not in there. So in this case, I would want to show that it's an odd number because the opposite kind of scenario of an even number is an odd number. So let's look at some observations. So all my prime numbers are, for example, 3, 5, 7. 8 is not prime because I can use 4 times 2 to get 8. 9 is not prime because 3 times 3 is 9. 10 is not prime because I can use 5 times 2. 11 is prime. 13 is prime. 14 is not prime because I can use 7 times 2 to get 14. 15 is not prime. 16 is not prime. 17 would be my next prime number. So my observations are the sum. I'm going to add them together. And the answer has to be not even. So I'm just going to randomly take two prime numbers. I add them up. I get an 8. That's not even. Or sorry, that is even. And that satisfies the conclusion. That's showing that the conjecture is true. If I take another two numbers, 3 plus 7, I get 10. This is also even. So I want to find one that gives me an answer that's an odd number. So let's take, for example, also I missed a prime number. 2 is a prime number because 1 times 2 is 2. So if I take the prime number 2 plus the prime number 3, I get the answer 5, which is not even, it's actually odd. So that's going to be my counterexample. So 2 plus 3 equals 5 is odd. This is my counterexample. So we have the condition 2 and 3 are prime numbers. And then my answer is not even. So that's what I'm looking for. So this example right here, I'm just trying to find an example. This counterexample shows that my original conjecture is false. So this means that even though some of the examples are true, like this one and this one, the conjecture itself is false because it's not true for every single example we have. Okay, so now I'm going to let you try some examples and then I'm going to show the solution to these examples in a video as well.